know, little icy pops.
Oh my god, the
Flavor.
Flintstones ones.
Ooh, this is a good one.
Well, just like
Ooh,
the
and a
regular
How do I
flavor.
put it without number squid?
All right.
According to Einstein, it is.
Who wishes to share one of the things they have written down? You would like to share? Go ahead.
We do.
Share.
That's what we know about relativity.
Relatives, moms and dads, brothers and sisters, they have something in common. Or,
That's what we
very
know
well.
about
You get a card. Okay, who else?
Hey, I
Yes,
can't
what's yours?
a card.
We have a bunch.
We have a bunch. Each person's reality is different or relative. That is, constant time is related to the level of interest involved. Possible to travel in time. E equals MC squared. The faster you go, the slower you age. These are very good. You get one. You already got one. You don't get another.
No, I passed it.
I didn't get
I'll give
one.
you another.
I want one.
You can have one too. Yes. What is yours?
Physics is the same for all inertial observers. The speed of light is the same for all observers, no matter their relative speed. And I remember something about squids.
It wasn't open book. It wasn't open book.
Wasn't it?
It wasn't.
That's okay. I did not say it wasn't open books. Therefore, if I do not say it, it is okay. Let us break this down very simply. Many of the things you have given me are correct, but we can make it even easier because you're getting into some specifics, and we don't need to do that yet. First of all, let's look at what relativity is. Relativity is very simple. I can pretty. Hold on. And this? Oh, you are so nice. I'd give you another card, but I don't. You already have one. I could give you an action figure. All right.
I didn't know they made Einstein action.
Maybe under the Christmas trees, everywhere this Christmas, the hottest thing on the market. First of all, relativity applies to the macro universe.
Oh, you did give me one.
Now, what do you think that means? The macro universe.
The big picture.
The big picture. Bigger than what?
Bigger than
Everything.
Earth.
Universe. The
Universe.
solar system.
Bigger than, you're thinking too big, Lucy. You're thinking too big.
The Earth.
You're still thinking too big.
The atom. A cell.
Ah, bigger than the atom. We are looking at things that are bigger than an atom. We are looking at the macro universe. We are also looking at a theory that is concrete. It is observable, it is measurable. We can define certain values and come up with specific information. We're also looking at something that is mathematical, but the math that is included in relativity is specific. There are no symbols with various meanings or variable meanings or undefined meanings. Basic mathematical concepts. You mentioned one before. You mentioned that E equals mc squared. Do you know what that means?
Energy equals mass times the speed of light squared.
A mass of what?
An object.
You are very good. You're very good. If I had another action figure, I'd give you that too. It is the mass times the speed of light squared of a non-moving object. Anything that is moving has more energy because it is moving. But the lowest energy level would be something in a completely dormant state. No initial movement. That's my point.
So wait, is there anything really in a really static state? I mean, aren't electrons and stuff always moving around?
We will approach that question.
Okay.
We will see if we can determine whether something is not moving or even if we can tell if something is. Finally, there are two key areas to relativity. Space-time and gravitation. That was made by my good buddy Sir Isaac Newton. Wonderful man, great physicist, made the best cookies, got those figs in there, the fig Newtons. All right, so we've got four basic ideas we're going to look at. Now, first of all, what we're going to do, you're going to do with me as I look at my sheet here to see what we can do. I think we're going to start with light. You see, what you pointed out was correct. We all see the same laws, but we see them differently, depending on the space and the time they are in. We are going to do a gedanken. These were one of my favorite things when I was alive. A gedanken. A gedanken is a thought exercise. We're going to do a thought exercise. So let's do one first, shall we? I think we need some volunteers. I have some here in my box. Now, as we look in here, we are going to have a ball. Would you hold the ball for me? Thank you. Now, we are going to say that Ringo and George, they are in, okay? They are sitting with the ball. They are in the yellow submarine.
Where do you find this?
Now, Ringo and George, Ringo is sitting here, and George is sitting here, and they're in the yellow submarine, and Ringo's going to bounce the ball, just like that. What does George see when Ringo bounces the ball? I want you to take your whiteboard. I want you to draw a circle for where the ball starts. I want you to draw a circle for where the ball stops. And I want you to draw a dotted line in between the two to show the path of the ball, as George sees it. Okay? Starts here, we will let it stop on the ground. We will say this is a very heavy ball that will not bounce back up. So I get the ball and I let it go. I want you to trace the path of the ball. One circle for where it starts, one circle for where it stops, dotted line between the two. What does George see? Very good. Oh, outstanding. Excellent, excellent. Now, here's our sort problem. Oh, by the way, if you need one of my posters, they'll be available after the performance. Now, we will have John and Paul. They were talking. John says, "Oh, tell me why you cry and why you lied to me." And Paul says, "But I want to be a paperback writer. Come and read my book." But they are standing over here, right? They are standing here. Would you be happy to hold Paul and John for me? Now, they are watching this yellow submarine. Our yellow submarine is traveling at 100 miles an hour. And in the time it takes Ringo to drop the ball to the ground, the yellow submarine will go from here over to here, as John and Paul will see it. Once again, Ringo is going to drop the ball one time, only once. I want you to tell me where the ball starts, where the ball stops, and draw a dotted line between the two. Remember, the yellow submarine is going, and they can see through this baby. It is a translucent yellow submarine. It is going from here when the ball is let go by Ringo, and when he finishes, the yellow submarine is down here. What do Paul and John see? I want you to draw the picture with the line attached.
Not to them,
If it bounces back up, that's very good. If it just drops to the ground, it is very good. You're a little slow over here, aren't you?
Oh, because they're on the boat.
You're going to have to get you some drawing practice.
Yeah, the ball.
This is Paul.
Let's see how yours is looking. Yeah.
They're looking.
That was very scary. Jack the Ripper once threw balls like that. Okay, so if the ball starts over here, and the yellow submarine is over here when it stops, the ball is actually, but the ball, when George looks at it, goes like this.
Right.
Is it a different law?
Their perspective is your
Where they are in space and time makes them see it differently, yet the ball is following the laws of physics the same way for both of them. Okay, that was very good. You did one very well. We shall try another one. You were talking about, could there be anything that's perfectly still? I want you to wipe your boards clean. I want you to look around the room, and I want you to list everything on your whiteboards that is moving. Everything in this room. Now, if there are people moving, don't write all of their names. It would take you a month, and I can't be alive that long because I'm dead. So you can write just people, and that would cover all the people. So everything inside these walls that is moving, that you can see moving right now, you must see it moving for it to be moving. Write down everything.
Look at here, the light.
Not the
Do
computer.
you see the light moving?
Well,
If you do not see the light
We don't see the
moving,
actual waves, but we see the light.
if you do not see the light moving, you cannot write it down. You must answer the questions. We have ways of making you answer the questions. All right.
In the room?
I have autographed copies of my book afterwards too, so they'll be available from. Okay.
What else is moving?
All right. How many things do you see that you can specifically identify as moving in the room? I will give you
Screen stuff.
The
15
flag is moving a little
seconds.
bit.
Oh, yeah.
Flag.
You heard us.
All right, let me see. What do you have? Hold up your white cards for me. What do you have? What do you have? Flag. Oh, the computer mouse. Was it moving? It was moving. Then people, the flag. You didn't have.
Oh,
you
the
did
clock.
Good. Very good.
I got
Clock.
it.
Very good. All right. Now, did a chair? Which chair is moving?
Patty's.
Patty's chair was moving because she was moving it. Let's pick something like, how about this desk up here? Did anybody put this desk on their list?
No.
Is this desk moving?
Yes.
Not
But we can't
observably,
see
no.
it.
Is it moving? Do you see it moving?
No.
Then how do you know it's moving?
Because we know chemistry.
You
and
cannot
electronics.
tell if anything is moving by itself. There must be a comparison. Let's say I had you do this experiment, but I put you on an observation post on the moon and gave you a spyglass. And you looked down specifically at this desk for a long enough time. Would this desk move? Why?
Because the Earth is
See,
moving.
Now, let's say, but what you're standing on the moon, is that moving?
Yes.
Can you feel it move?
No.
Do you see it moving?
No.
But if I put you on Jupiter and gave you a bigger spyglass, would the observation deck on the moon be moving?
Yes.
So all motion, for you to detect it, must have a point of reference. All motion is relative. Let us try one more. I like the balls because the balls are so much fun. One of the things about space-time, and again, these are the things that are most important today. It's a macro universe that it's concrete, it has a sound mathematical formula, it's space-time. Let's imagine this is the Earth. When you walk across the Earth, do you realize you are walking on something that is curved? An ant walking on this ball, would it realize it is walking across something curved? It doesn't. Our thoughts of how space and time relate must be changed because we are perceiving things that our senses in normal space and normal time cannot accept. I'll give you an example. What I want you to do, I'm going to give you each one half of the box. And if you look in one corner at the bottom, there is a blue dot. There is in the upper corner, on the opposite side, an orange dot. Or red, depending upon which color I use. What I want you to do is write on your whiteboard, either draw it or write. I want you to put down what the straightest line is. The straightest path, we all know that the shortest path between 2 points is a straight line. What is the straightest path between the blue dot at the bottom and the red dot at the top? I will even give you one of these brightly colored, in some cases not, rulers to use so that you can plot the point. You can draw your answer, or if you prefer, you can write your answer. But I want you to write down or draw what the straightest line is, the shortest path between the blue dot and the orange dot. I will give you just a few seconds to think about it. Now, normally, if we were doing this in a 55-minute classroom, we would take more time to explore the possibilities. But for right now, which way is the best way to do this? Now remember, one is at the bottom, one is at the top. And if you are drawing a diagonal, how could that, let's say the ant was standing at that blue dot, how could the ant walk up a diagonal that is not there? What I want you to do now, you have your possibilities down there. I want you you see there's that box is folded in each corner? I want you to unbox it. I want you to make it a flat piece of paper. And then I want you to do this exercise again. Use the ruler. Draw a straight line and tell me what is the straightest path between the blue dot and the red dot, or the orange dot. Or if you are colorblind, the lighted dot. Once you hit 117 years of age, you don't see color so well anymore, let me tell you. All right. Straight line, the shortest path from the blue dot to the red dot. Draw it right on your box. Use your markers. Be colorful. Draw the straight line. And tell me, did the straight line go in a diagonal directly across the box?
What if your red dot got split in two?
Yeah.
No.
Pick the red dot to the left.
To the left.
To the left. Pick the red dot to the left. If your red dot is split in two. Ah! You notice if you drew the straightest line, did you go directly through the middle, the diagonal? Or did you perhaps go up part of the one side? Did you perhaps go up part of the one side?
Yes.
The straightest line was not a direct diagonal. It was a line up the side of the box. We must always think in terms of three-dimensional space. That is why, in postulating my theory of relativity, I pointed out that we cannot just say the shortest distance is a straight line. In space-time, space is curved. It is not straight. Therefore, the shortest path might not be the obvious straight line. All right, enough of the relativity. We had fun with it. It was a lot of fun. Ha ha. Time is up. Now we go to Quantum, a guide for the perplexed. This is not my book. It will not be for sale after the show is over. Quantum is a whole different beast because, first of all, I need another color. Oh, blue one. I like blue. No, we have blue one. That doesn't work.
We have one.
Here's a
We
red
have a blue one.
Do you have a blue one? I want some blue
Yeah,
one.
blue
I
there.
love blue. You don't get many kicks at my age. Yeah? Okay. This applies to the micro-universe,
Adam.
which we know is, and below, the smaller particles. Also, this is
You can tell he's Austrian. He spelled universe wrong.
it is undetermined. There are so many things that we can never know at any one time about the state of matter and particles in the subatomic universe. Quantum mechanics is based on the idea that all small subatomic items have both a wave and a particle function. It is based on mathematical formulas, but sometimes the formulas are just including variables that don't really have a design value. So we may not know what those numbers are. And as we pointed out, the two major areas, subatomic, and it deals with quanta, which are those particles that have a wave and a particle function. I have in the back of the room, to give you an idea of how weird this is, I have a box. My good friend Evan Schrodinger gave it to me. In it contains a live pussycat. I assure you that probably, but I'm not sure, no pussycats will be harmed in the conduction of this thought experiment. Now, inside this box is a pussycat, a cute little pussycat, a little Siamese pussycat. His name is Franz. And Franz is in there. He's got a little bowl and some cat toys to play with. He also has a small vial of prussic acid. And there is a small radioactive particle inside there. Now, when that radioactive particle emits a radioactive decay, it will break the glass, the prussic acid will come out, and the pussycat will go kaput.
Oh my God.
Now, here's my question to you. Right now, I want you to take your whiteboard, talk it over with your neighbor for a moment, and just guess whether or not the cat is alive or dead. Is the cat alive or dead? Only from the information you have right now that I am telling you. All you can do is see the box from here. Is that cat alive or dead?
Okay.
But if you tell me it's alive or dead, you must tell me why. I must go why. The cat is alive or dead. You said alive. Why is the cat alive?
Because the vial hasn't broken yet.
Do you see the vial?
No, I'm not seeing the vial.
How do you know the vial hasn't broken yet?
We're not
Because
dead.
we would all be dead.
Well, no, we have a lining inside here, so it. Oh, yeah. What did you say? Oh, you didn't even venture. I guess. Oh, I'm sorry. No more business cards for you. How about you? Dead. It's not making any noise. Maybe it's in a coma. What did you say?
Well, I don't know.
Ah, you don't know. This is the best answer. You see, according to quantum mechanics, the cat is both alive and dead.
Okay, so
And you cannot determine which it is. In fact, it will not determine which it is until you open the box. If you open the box, the cat might be alive. You close the box. You go away, think about 15 minutes, come back, look, and the cat might be alive when you open it again. And you close it, come back another half hour later, open it again, the cat might be dead. It doesn't matter because it's not in a specific state until you observe it. Now this poses a problem. This poses a problem when we go to observe it. This is the part you were waiting for. This is the food part. This is the end here. I need you to give everyone in the room, every person, one of those cups right there. Right? Would you do that? Take it. Or you can take the box out and pass it around. Yes, that will work just fine. And would you give everyone in the room a spoon? What you are getting is a mass dense that has 1, 2, 3, 4, or 5 small particles in it. What you must do on your white sheet is you must draw a picture showing me the exact location and orientation of the particles. The particles, if I had one here, would look like this. If you looked at them from the top, they are round. If you looked at them from the side, they are kind of like a flying saucer. You must tell me. Oh, you know, you may not put your spoon in there because once you put your spoon in, they're not in the same position anymore. See? So now, you must find out and tell me and draw that picture exactly where those particles are, what their orientation is. Are they at an angle? Are they at 90 degrees? Are they flat? Are they pointing up? You must tell me how many and what there are, but you cannot disturb the pudding.
Can I borrow your marker? Share. Oh, I didn't need more sleep.
This exercise is worth 100 points to your grade if you get it right, and it's worth 0 points if you get it wrong. You must tell me the exact position, the exact orientation, how many there are,
How many what are?
how many particles. There might be 1 or 2 or 3 or 4 or 5.
How are we supposed to know?
Because there's something.
Ah, the point of quantum is whenever you do any experiment, you automatically change the rules. Once you have put your spoon into there to see where the particles are, you no longer have the same thing you started with. So you can't give me an exact drawing. It's impossible. In the same way, when we look at waves and particles, it is impossible to see a wave. If you look for a wave, you will see a wave. If you look for the particle, you will see a particle. Now you may say to me, Albert, how could we do this? How could you say, if I look for something, I can only see one part and not the other? This is the very last thing I will give you today, and I hope you will enjoy it. There's I put my little envelope. I bet it's open there. There's one more thing we must do. I'm going to give you a little piece of paper, and I want you to look at it. I want you to notice the white dots. Do you see anything in the white dots?
Yeah, they keep changing into black.
Do you see the black dots?
Yeah.
I want you to look and see the black dots and the white dots. I want you to specifically look directly at and identify a black dot.
You can't. When you go to look at it, it disappears or goes.
You cannot do that? You cannot find the black dot if you look right at it?
If you look at a white dot, you see the black dots around it with your outer peripheral.
Just like in quantum mechanics, you cannot look directly for something and find it. We cannot find the exact momentum, the velocity of an electron, and know where it is. But if we know where it is, we cannot find its velocity. It's the same way with your card. You can know there's black dots, but you can never see one. But you can see the white dots, and when you do, you still know that there's black dots, but you can't actually see it. Quantum mechanics has variables that do not allow us to know specifics at any one time. I give you this brief outline as my going away present. These are some of the key points of relativity and quantum. But for today, what we need to remember, relativity is for the macro universe, The micro-universe belongs to the quantum mechanics. Relativity is concrete, mathematical. There are no questions. We know what is happening there, but when we look at quantum mechanics, we have a lot of undetermined values that we are not aware of. We can see in quantum mechanics things are waves or particles, and we can't necessarily see them as both at the same time. We can only see them as one. And we know that this deals with the subatomic. It deals with small pieces called quantum, which share a dual nature of waves and particles. That is it. It's finished. It is done. Questions? No? Good. Thank you. Goodbye.
Ringo's bored on his submarine cruise.
Can we use this pudding?
Yes, the pudding you can eat.
What's in there?
M&M minis.
Oh, okay.
Oh,
America's
what
favorite.
else?
America's favorite. No, that's
To
it.
make more exploding.
You know what? Just did.